All right, remember that this information is not on the test, but it's going to help us to be able to do our lab next week. So we are focusing on another way to measure concentration, which is going to be molality. So molality is usually used for chemical applications that are temperature dependent. The equation for molality is molality, lowercase squiggly m, is moles of solute, so just like molarity, over kilograms of solvent. The numerator is in moles. You may have to use molar mass to convert grams to moles, and then you should know that there's 1,000 grams in 1 kilogram. So let's do our first problem here. What's the molality of a solution of 10.0 grams in 500.0 grams of water? So my equation for molality is moles of solute over kilograms of solvent. I'm going to identify my solute, and I'm going to identify my solvent. So I'm going to convert my 10.0 grams of NaOH into moles of NaOH. I'm going to use molar mass of NaOH for 1 mole of NaOH. And the molar mass is 40.0. And in my calculator, I'm going to get 0.25, but sig figs, I get 0.250. So I'm going to put that in the numerator. In my denominator, I need kilograms. There's 1,000 grams in 1 kilogram. So that's 0.5000 kilograms of my solvent, which is water. So now I put that down here. And that's going to give me 0.500 molal of the solute NaOH. Another problem that typically you will find with molality is that they want you to find the kilograms of water that should be used to make a solution with so many grams of the solute. So once again, this is my solute. This is my solvent. So we start with the equation. Molality is moles over kilograms. So I have 0.75 molal equals the mole amount. So I got to figure that out. 90.0 grams of KNO3. Grams of KNO3. Mole of KNO3. The molar mass is 101.1. And then with 3 sig figs, that's going to be 0.890 moles of KNO3. So that is going to go in my numerator. And this is my x, my kilograms. Cross multiplying, 0.75x equals 0.890. Solving for x equals 1.2 kilograms of H2O. So now that we know molality, we can look at colligative properties. Colligative properties are properties that are dependent on the amount of dissolved particles, not on what type of particle. There's 3 of them: vapor pressure lowering, boiling point elevation, and freezing point depression. The vapor pressure determines the boiling point. Remember, vapor pressure equal to the pressure of the liquid is going to make the solvent boil. So a lower vapor pressure means you need a higher temperature. To get it equal to atmospheric pressure. So if you add salt to water, there's a common misconception that people think that it boils faster. And that's not true. In fact, it's going to make it boil higher than 100 degrees Celsius. If you're adding salt to any water for boiling purposes, it's because you're adding salt to the water maybe for flavor, but not to make it boil faster. That's a huge misconception in science. Freezing point depression. So this is what we need to know for making ice cream. Solids form when molecules make an orderly pattern. But for some reason, if a solute breaks up into particles, specifically ions, it's going to lower the freezing point. And the reason why is because now this solvent that used to be pure can no longer make its crystals. It has to deal with these extra particles that are in there. So salt water freezes below 0 degrees Celsius, and this is how ice cream is made with rock salt. So, colligative properties. Some particles in solution will ionize or split, while others may not. We already know that ionic compounds dissociate into the ions that they form. Molecular compounds do not dissociate. So here are some examples. We're not going to do these or this one. But as the number of particles increase, the greater the effects on vapor pressure lowering, boiling point elevation, and freezing point depression. So between these two, sugar and potassium iodide, potassium iodide has more particles. It's going to make the freezing point lower. It'll decrease the freezing point more if I add potassium iodide versus sugar. Why? Because there's more particles. So, question here, you have 500 milliliters of 1 molar solution of NaCl, Na2SO4, Na3PO4, and Al2SO43. Which solution would have the highest boiling point? So, you have to know what ions they separate into. This is Na plus, Cl minus. One particle here, one particle here. The I value is 2. Here, this is Na plus with sulfate. But there's 2 Na positives to cancel the sulfate. So I equals 2 plus 1 is 3. Na once again is a positive. Phosphate is PO43 minus. I need 3 sodiums to cancel. So I equals 3 plus 1, which is 4. And this one here, Al is 3 plus, sulfate, SO42 minus. There's 2 aluminum ions, 3 sulfate ions. 2 plus 3, I equals 5. So of these 4, the one with the highest I value is going to have the greatest effect on colligative properties. So if I had some aluminum sulfate, this would cause the highest boiling point compared to NaCl, which has the lowest. Now we're on page 14. So now we're going to look at colligative properties and the equations that we can use to figure out the difference in the boiling point or freezing point when we add a solute to a pure solvent. Adding a solute raises the boiling point of the solution. Finding the change in the temperature of the boiling point is going to make it so that it's a higher boiling point, so we have to add it to the boiling point of the solvent. Here's our equation. Kb, which is a constant, M is molality, I is the number of particles. So Kb is the boiling point constant of the solvent. Remember, these notes are not on the test, so don't worry about that. Molality is M, I is particles. Freezing point depression, which is the one that we're going to use for the lab, adding a solute lowers the freezing point. So we're going to find the change in the temperature of the freezing point and subtract it from the freezing point of the solvent, usually water. So this is the same equation, but it has a different constant. And this one we add it to the boiling point, this one we subtract it from the freezing point. So here's the problem we're going to do. First thing though is we're going to change these sig figs. We're just going to keep it to 1,000 with a decimal. So use a table. below to answer the following questions. Calculate the molality. Well, NaCl is my solute. This is my solvent because I have water. NaCl, aqueous, separates into Na plus, aqueous, and Cl, 1 minus, aqueous. So that's going to give us an I value of 2. We're going to need that. Now, we're going to calculate the molality. Molality is moles of solute over kilograms of solvent. So, I need to first find the moles of solute, so I'm going to take 150 grams of NaCl, convert that to moles, and that gives us 2.6 moles. A 1,000 grams, there's 1,000 grams and 1 kilogram, so that's exactly 1.000 kilograms. So this is going to be 2.6 molal of NaCl. So I found my molality. Now we need to find the delta TB. So that's the change in the boiling point. And then we're going to add delta TB to the boiling point of H2O. So delta TB is Kb times M times I. The Kb for water is 0.512 degrees Celsius per molality. I know my molality is 2.6. My I value is 2. This is unlimited sig figs, 2 sig figs, 3 sig figs. So I'm going to round to 2, and I get 2.7 degrees Celsius. So I'm going to take 2.7 degrees Celsius, add that to 100 degrees Celsius. This one here is unlimited. That gives me 102.7 degrees Celsius. That is my new boiling point when I add 150 grams of salt to 1,000 grams of water. Now we're going to find the freezing point. Delta TF gives me Kf times M times I. Now we're going to subtract this delta TF from the freezing point of H2O. So here we have Kf, which is 1.86 degrees Celsius per molality. Molality is 2.6 moles. I value of 2. So when I put that in my calculator, I get 9.7 degrees Celsius. So I'm going to take the freezing point of water, 0 degrees Celsius minus 9.7 degrees Celsius. This is unlimited sig figs, so it's negative 9.7 degrees Celsius. So if I add 150 grams of salt to a kilogram of water, it's going to lower the temperature to negative 9.7 degrees Celsius, much colder than 0 degrees Celsius. Last possible problem that you may see, it's actually probably one of the hardest ones, is this one. So remember, we took this out of the test, so you don't need to know this for the test, but I feel like it's important for you to see it. So in the lab, the boiling point of a solution of a non-electrolyte was determined to be 102.5 degrees Celsius. 570 grams of the unknown non-electrolyte was dissolved in 1.50 kilograms of water. What is the molar mass of the unknown substance? Why does it matter that it's a non-electrolyte? Because I is 1. They want us to find the molar mass. So molar mass we know is mass, so grams over mole. And they already told us that we have 570 grams. But I don't know the mole amount. So I have to use the information in the problem to figure that out. First thing I have to do is find delta TB. Well, delta TB, now the boiling point of the solution with the dissolved non-electrolyte is 102.5 degrees Celsius. So to figure out what that delta TB is, I'm just going to subtract the water, it's boiling point. So 2.5 degrees Celsius is the delta TB. Now we're going to find molality using delta TB equation. So that's our equation. We're going to plug this information in. 2.5 degrees Celsius equals Kb, which we have on the previous page, 0.512. Molality is my x. My I value is 1. X equals 4.9 molality. Now I'm going to find moles using molality. Well, molality equals moles of solute over kilograms of solvent. My molality is 4.9 equals mole is what I'm solving for now, and my kilograms of water is up here, 1.50. So when I solve for x, remember x equals moles, that's 7.4 moles. So I did step 2, step 3 to figure out the mole amount. Now I'm going to put that in the denominator for molar mass. Divide these two numbers and I get 77 grams per mole, and that's my answer. So this concludes the notes for molality and calculations that deal with molality.